a table like this. I would make a table of n and q, and then try a value for n, see what you get for q, etc., etc. Always start with 0, right? For the 0 number of points, that's a possibility also. And number 9 was the other one more you had trouble with?
Yeah, because
in exercises 9 through 12, the digits. Okay, this is kind of like the example we ended in class. But we never got to. So look at the digits of a positive 2-digit number or 2-digit integer n are interchanged to form an integer k. Find all possibilities for n under the conditions described. So how did we do this last time? Do you remember from class? We kind of ran out of time, but what did we do to start the problem? It was an important fact that we started the problem. It was useful too. For the interchanging number, we said, you know what, we could have numbers here to switch the values, but we have to do some sort of a method here with variables. So if you remember, I called it like xy, or I think in the video, I think I called it like U for units and T for tens, something like that. So I would start by doing that first. It says the digits of a positive 2-digit n are interchanged to form k. So this is n first, and then the value of k would be the following, right? K would be yx. It says n is odd and exceeds k by more than 18. And it says find all possible values. So there's going to be many possible values here, right? So if n is odd in this case, we have to consider the fact that y, the value y can only be 1, 3, 5, 7, 9. That's a limited domain again. Think about y. Y can only be odd if n overall is odd. Now here that means that this value is going to be either like in the teens, or in the 30s, and the 50s, and the 70s, or in the 90s. This can't be in the 60s or 40s, because that would put a 6 or a 4 here, which would put this to be 6 or 4, which it can't be because it's odd. So right away, let's jot that down, that y can equal 1, 3, 5, 7, or 9. That's the first statement. Again, if n is odd, that's what y must be. The next part again says that that n exceeds k by more than 18. So let me jot this down in this terms first. N by more than 18. So it's really, we would say, greater than or equal to k, or actually just greater than in this case, because it exceeds it by more than, not more than or equal to. Plus 19, 18. So that's kind of all we know right now. When I'm looking at n, the value of n, I have to use x and y here. And when I'm looking at k, I also have to use x and y. So watch what I'm going to do, and this is where it gets a little bit tricky. Think about numbers for a second. This is what Helen said a minute ago. Put numbers in here. Think about like the number 32. The 3 for the x represents 3 times 10, really, to give me 30. And the 2 that's under the y represents 2 times 1 to give me 20. Does that make sense? That's how I'm doing the values of places. So x is really not just the value of x. It's x times 10. Because the 3 represents really 3 times 10 for 30. So x represents x times 10. So where I see an n, I could put 10 times x here plus 1 times y. Again, because x, when it's in the number n, represents the tens digit, so 10 times whatever x is. And this represents the ones digit, so 1 times whatever y is goes there. And then for k, what do you think I'm going to do for k? How do I go about k?
2y plus 3x.
Where are you coming up with the 2 and the 3?
It would be, if the percentage would be 23.
But let's forget the 3 and 2 now. Go back to the values. How would I do it algebraically on the right? So make believe I didn't have the 32, right? So this is what gave me this because it's worth 10. And this gave me this because it's worth 1. So how would I do it for k now, is what I'm saying? What would the values do if I switched the values here? What would it look like for k? What would I plug in for k over here?
10y plus 1x.
Yeah, so I'm just switching those values. You did it. That's exactly what you did, Alan, but I wanted with the variables, not the numbers. So we switched them here. So now this is in the 10 spot. So that's a 10y. This is in the 1 spot. So that's a 1x. And then we have a plus 18 on the end still. So although this looks complicated, this is the same thing as what we did on Friday because it's two variables, but instead of one equation, we have one inequality now. We still do want to collect our terms, right? We want to collect our terms still. So I'll take the 10x minus the 1x to make this a 9x. So that's by moving this 1x over here. I'll move the 1y over here by subtracting it. That makes that a 9y. And then I still have a plus 18. Again, you're doing the same step, right? Moving over to do that. What am I going to do right now at this point? What makes sense? What's logical in this problem? You have to see it, right? Inspection. What do you see? Divide everything by 9. It just makes life so much easier. Oops. So this is my relationship for the values of x and y pretty much. So the y value just has to be the x value has to be the same as the y value, but 2 more. But more than that now, right? Not equal, but more than that. You all see what I'm saying here? It's no longer equal, but it's more than. But I also have restricted possible values. So I have to consider my options here. So what can I, God bless you, what can I plug in for y? Because normally I would say try 1, try 2, try 3, try 4, and get the other value. That's what we've been doing the whole time. But I can't plug in every number for y. What can I plug in for y? Odd numbers, because that was the first restraint we had. Our values of y were restricted to odd numbers because y represented the units place here in the number n, which had to be odd as our first statement. So try 1, 3, 5, 7, and 9 here to see what x would turn out to be. But recognize that I can't plug 9 in here. Why not? What's 9 plus 2? It's 9 plus 2. And x is a single-digit number here. We know that because x came from a spot, right? X cannot be itself a 2-digit number. X is 1 digit of a 2-digit number. So x cannot be a 2-digit number. So 9 will not work in there. 1, 3, 5, and 7 can work. But could 7 even work? If I plug a 7 in here, I get the fact that x must be greater than what? 7 plus 2 is 9, right? X must be greater than 9. Is there a single digit number that exists that's greater than 9? No. Every number greater than 9 is 2 digits. So 7 doesn't work either if I try 7 in here because of the greater than sign. If this had been an equality, right? If this had been an equality, 7 plus 2 is 9, then x could have been 9. That would have worked. But I cannot plug in, again, 9 or 7 for y. So now I have to try 1, 3, and 5 only at the top there. So I get 3 possible values. What am I trying to find in the end? Find all possible values for n. So x comma y is what we're looking for. So if I were making a table of values, 1, 3, and 5 are what I'm trying for y. And therefore x must be, if y is 1, what could x be? This is really a little bit even more confusing now. If y is 1, what could x be? Plug in a 1 for y. What do you get, Mauro?
3.
No, you don't get 3. What do you get? What's the statement? Be careful. X is greater than 3. So what could x be, Mauro?
It could be 5. Oh, wait, no, it could be 4, 5, 6, 7, 8, 9.
Right? So x can be any number from 4 to 9. Again, plug in a 1 for y. You get x is greater than 1 plus 3, 1 plus 2, 1 plus 2 is 3. If x is greater than 3, it could be 4, it could be 5, it could be 6, 7, 8, or 9. And x could be odd or even. We don't care about that. And the same goes for the next part. This will be 6 through 9, because if you add 2 to that, it'll become 5. And the next one will be 8 through 9. So we have a lot of possible values for n, because n was defined as what? N was defined as x comma y. So how many values are we going to have here? We could have 41, 51, 61, 71, 81, 91. And we could have 63, 73, 83, 93, and then finally 85 or 95. And the answer makes sense because all those values of answers here in red are all odd. That holds true to the constraint that we started with, that n is odd. And we also recognize that when we switch the numbers, we'll get one of those values where n is greater than k by more than 18. So if I switch 91, what does 91 become? 19. 91 minus 19, that's going to be more than 18 as a difference. That's the second condition we have to meet. So switching those unit values, or these placeholders, these tens and unit values, still holds this true up here at the top. Okay, where the first thing must have been greater than the second thing by more than 18. It's not the easiest topic, right? You notice that? Because you have to think outside the box. You're applying, what are you doing? You're applying weights to different values in a number. So if it was a 3-digit number, you have the units digit, which would be x, the tens digit, which would be 10y, and then if I call the third one z, I have to put 100c in front of it, because the third value of a 3-digit number, or the biggest one, represents the hundreds place. So this kind of goes back to like literally second and first grade. Remember in first grade when you talked about units place and tens place and hundreds place? You were like a really small kid, and sometimes your teacher would give you stacks of cubes, and every stack of 10 would represent a tens place, every one would individual units place, and then you would get like a block of 100, which represented a hundreds place. That's what you're doing here every time. Okay, if you're confused on this and you're still not certain, please come see me. Okay, because you have the one example notes and now this one. So if after 2 you're having trouble still, we can go over a couple together, but I'm not going to continue on this one anymore. Okay? All right. So what I'd like to do is start. The first one here is draw a graph of the equation 2x plus y equals 7. And this is the method that I told you we're really never going to use. Right? We're never going to use this method of graphing by plotting points. But we really should know where a graph comes from. So we'll do that once right now to show where it comes from and how it's a possible list of solutions. So to do that, I would simply do what we've been doing all along. Make an x and y table. It doesn't matter what values you choose. When I'm graphing and I'm actually picking points, which again is really never, I would choose points like these or something that's reasonable, because I don't know much about this graph. I'm going to choose the origin and points about the origin. It might make sense later on in this course to choose points about other locations like x-intercepts or what are called asymptotes or holes in the graph, and we'll talk about specifically choosing points along the way that are strategic.
Can you put it in the slope intercept?
Yeah. So again, we're going to see that we've done that. But if I actually ask you more graph by, which I'm not going to do in the test, but if I said hypothetically graph by plotting points, I want to see graph by plotting points. So for now, just do it that way. But yes, you absolutely can put it in slope intercept. Okay, and it would be a little more logical to do that anyway. So y is equal to 7 minus 2x, and I can plug in for x. If I plug in negative 2, I'm going to get 11. If I plug in negative 1, I'm going to get 9. And I'll notice they all go down by 2. Again, I can see that because as Laura pointed out, we can simply use the slope as negative 2 and see that they're going down by 2. The y-intercept, if I know slope-intercept is 7, and look at the coordinate 0, 7. Remember, the y-intercept exists when the x-coordinate is 0. So these are my 5 coordinates here. One thing I'm going to encourage you to do at this point is to take a screenshot or save like a JPEG to your camera roll of an x-y axis with the grid line. You're in Notability, so you can change your background to grid lines if you want to. But something I've done, I just save it as like an existing image or a video or something like that. I'm trying to think of where mine would be. It's probably under File, actually, for me, yeah. But I just save like a quick screenshot or a background of a grid to always have a graph there. And of course, it's not showing up for me. That makes sense. Here we go, there it is. So I'm simply plotting 5 points here, that's all I'm doing. Negative 2, 11. What am I going to go by on my y-axis? If you were graphing on these axes, what would you use your instruments as? This is our first time we're really graphing stuff. If we go by what values would make sense logically here? Logically, what would make sense to go by values of? On the y-axis, Mauro?
2.
Yeah, because I need to get up to 11. This is something that is really not pushed as much and not really like hammered on when you're younger. You got to be able to choose the right values of increments. Here, because my max is 11, and I look at the graph I'm seeing, I'm going to go by 2s so I can get up to 11. It's not going to help me much down here, unfortunately, but that's okay for now. And then along my x-axis, I'm probably only going to go by 1 because I don't go very far along the x. And I can do that. As long as I put one increment down, I'm okay. So I can do that, and label x, and label y. Okay, and that's fine. From that point on, I know my graph's not existing. This feature is known. I'm going to go by 1s here. I could even go by 0.5s on the x-axis, so I want to really spread out the graph a little bit more. But I want you to recognize something. When you guys graph on your calculator, because so many students now rely on the calculator to graph and don't know how to graph. I'm telling you. And I've seen students like older than you that progress through thinking they know how to graph, but all they do is always type it in. This is not the window you're going to see. On your calculator, defaults to go 1 by 1, or 1 increments, and go negative 10 to 10, negative 10 to 10. So recognize that you're going to stretch your graph accordingly, and your graph looks different based on your actual increments. So when you get to graphing other functions like trig functions, you might want to stretch or dilate them in different directions to see the full graph. And recognize that you're doing that by changing these increments here. Negative 2, 11 would be up 1, 4, 6, 8, 10, 11. Up here. And then I'm going down by 2 every time. So those are the only 5 points I have on this graph. And I go down by 2, which is simply a full box length in the vertical direction. I go over by 1. Down 2, over 1. Down 2, over 1. Why is my graph decreasing? These are questions that we're going to really answer in the next couple lessons. But why is it decreasing?
Because the slope is negative.
Yeah. Slope being negative means the graph is a decreasing function. Okay, and I would use a straight edge if I were a student and I were taking this on a quiz or a test. If I didn't have a straight edge, I'd probably just use my ID card, right? To make a straight line. Any questions on this by points? You're really going to see this now and probably never use it again. Take the slope intercept or graphing by intercept method, using the x and y intercept is another method that's a lot easier than using points. Points take too long, and I would never use 5 points. How many points do I need to make a line? How many points do I need to make a line? This should be an automatic answer. Everybody should give. What do you think, Sebastian? 2. Just 2. Okay, any 2 points connect to make a line. So I do not need 5 points in reality. Is that clear? But how many points do I really have on this line? What is a line really considered? How many points? Infinite, right? A line is infinitely many points. That's what it is. Just stacked next to each other. So let's go ahead and look at the second example. So this is the one that's, I think, really more important, which is called graphing using intercepts. And you guys know how to do this. You've done it already. When you want to find the y-intercept, you've been told set x to 0. When you want to find the x-intercepts, you've learned set y equal to 0. And that's what we're going to do right now. Intercepts are where they cross the axis. The axis is where the other variable is 0. Again, if you want an x-intercept, it's where you cross the x-axis. That's when y is equal to 0. So just set the opposing variable equal to 0 to find your intercepts. So let's do it for the first one here. So if I'm setting x to 0, the equation becomes this. That's it. Literally, when I set x to 0, I get y equals 3. Well, what is that? That's really the y-intercept. So there's my y-intercept. And then I do the opposite. I set y equal to 0 to get the x-intercept. But notice, how am I writing my answers? I'm writing them as what? I'm writing them as coordinates. They are coordinates. Please, if I don't see that, I swear I'm going to take off points even though it's small. Here's why. Let me explain. Not just to be irrational and angry. The reason is this. So many students write it as x equals a number and y equals a number. That's not a coordinate. That's the equation of a line. We're going to talk in a moment. You're going to see that x equals is really just a vertical line. And y equals is just a horizontal line. And we'll see that in a minute. So you cannot leave it as x equals and y equals when you're finding intercepts. Please write it as coordinates the correct way. This will come back to bite you in calculus on like an AP exam. You will lose credit left and right if you don't write it the proper way. Okay, your notation is very important. So this graph is really easy. I'm not even going to use my loaded my grid lines because I don't need all those grid lines here. This is an easy graph for me to graph. All I have to do is plot the x and y intercepts and I'm done. So x is equal to 4.5, negative 4.5. And y equals 3. And then I'm just going to connect those 2 points. And there's my line. If I have multiple lines on the same graph, I should probably use either multiple colors. If I'm doing it on like a problem set where I have colors, I should use one solid line. What should the other one be then? Dotted or dashed. Or I could even just label all my lines. But because I only have one line here, and I'm graphing one equation from the beginning, I don't really need to label this as much. Okay? And if I say as much, meaning like, if I'm not unclear about what it's showing, there's no need to label it. Okay, there's no need to label the line on the actual graph because it's written right above.
Do you want us to, like, on a regular graph, like the last one, do you want us to, like, label all of the points?
No, you label the first increment, the rest are all the same. You can't change increments, so by default, if you were to label them all, it's just doing extra work. So if you label a 1 here and a 1 here, Mauro, that's sufficient right there. That's what you should label, a 1 and a 1. But all those points along the way that you plotted, label all those points, I can see them on the graph. There's no need to do it. I might say, identify on your graph the vertex. And for that spot, for a parabola, when you do a parabola, you make it the point and label the vertex with a word. Because I want you to understand the vocabulary and how it refers to the graph. That's totally different. But labeling points with coordinates themselves, unless it's specifically requested, is not needed.
And we don't need to label like
I mean, what I've shown here is more than sufficient. So if you can label your increments as 1 and 1, I know that every tick mark is a number 1 here. Maybe tick mark every 5 if you're going to a really wide graph so that the user that's reading your graph could see every 5 or so. That could be useful at times. But because of the range and the domain here, which are all real numbers, but because of what you're seeing here, sorry, it doesn't really matter as much. I didn't go as far in the X and the Y direction. So this is called graphing by intercepts. It's really useful and it's really underrated and underused. Okay, it's actually a lot easier when everything, write this down please. When things are given in this form at the top, that's called standard form. When a problem is given, when an equation of a line is given in standard form, it is a very useful technique to graph by using the intercepts. Because all you got to do is cover up the missing part. Whatever you're setting equal to 0, you literally would just be covering up. So if I'm thinking about doing this, here's what I'm doing. Ready? When I want the y-intercept, that's what I do. I literally cover up that, and that gives me the y-intercept, right? When I want the x-intercept, I literally cover that up, and that gives me the x-intercept by solving that. So with my hand, if it helps, I'm literally just doing that to get the intercepts. So it's a very useful technique so that I can quickly get the intercepts and graph the line. These are our horizontal and our vertical lines, and we call them constant functions when they're horizontal. We don't call them that when they're vertical. And we'll talk about why that is when we talk about functions, but some of you probably know that already. How would I write an equation of a line or draw an equation of a line like this? Y equals 5. For example, if y equals 5, what could x be? Right? Because any coordinates, if I try to visualize what a line like this looks like, what could my coordinates be for the line y equals 5? Give me one of the coordinates for the line y equals 5. One coordinate. 0, 5. That works. So let's put that. That's right here. Here's 0, 5. Okay, that's one coordinate for the line y equals 5. Give me another coordinate for the line y equals 5. 1, 5. That works. Let's put that right here. Give me another coordinate. Negative 2, 5. What do I notice? Everything has a y value of, because the equation says y equals 5. So by definition, when y is always equal to 5, that's an infinite amount of points next to each other like this, which really just creates a line. And that's the equation y equals 5. So that's why it's really important that you don't write your intercepts as x equals and y equals, and yet you write your intercept as an actual coordinate, as a coordinate itself. And what about x equals negative 7 halves? Please don't confuse that with a slope, right? If you need to, rewrite it like this to start. What's x equals negative 3.5 going to look like? What's that going to look like? Isabella? A vertical line going through where? Yeah, it's a vertical line going through the x-axis at negative 3.5. So draw a vertical line going through that blue dot. So it's an infinite amount of points stacked on top of each other and below, creating a vertical line, and that is x equals negative 3.5. Okay, these are just, I'm trying to show you that this is like an infinite amount of little points. It's really a solid line, okay? It's really a solid line. So horizontal lines are called constant functions because by definition we haven't gotten to really the term functions yet, but a lot of you know what they are. Functions can only have what? Can only have one y value for every x value. If you don't know this yet, it's not a big deal. We're going to get into functions. But for a vertical line, unfortunately, for this x value, it has multiple y values that can come out. But for this line here, for every x value, there's only one y value. For this x value, there's only one y value. But this is not called a function here. But this is called a constant function. Because this is like a function that isn't changing. It's constantly equal to 5. Finish up this for night, please.